All right, we're back for stoichiometry part two, where we're really going to get at the heart of what stoichiometry is about. We're going to talk about mole ratios. We're going to talk about stoichiometry map. So if you remember from last time, we had this equation, barium hydroxide reacting with phosphoric acid. This is the acid-base neutralization reaction. And when we do stoichiometry, what we're trying to do is convert between some quantity of a known compound to some quantity of an unknown compound. And so if you notice, there are four chemical substances, four reagents in this reaction. And when you're doing stoichiometry, you can only really deal with two at a time. So you're always going to want to try and identify your known and your unknown. And once we do that, if we have our moles of known, we can move to our moles of unknown. And this is really the center of stoichiometry. How do we do that? Well, we do it with what's called the mole ratio. And the mole ratio is just the coefficients in the balanced chemical equation. So the mole ratio from barium hydroxide to water is 3 to 6. The mole ratio from barium hydroxide to phosphoric acid is 3 to 2, and so on. So here's a problem that you might be faced with. How many moles of hydrogen phosphate are required to react with 2.71 moles of barium hydroxide? So you're going to want to identify your known and your unknown. Your known is that thing which you are given information about, in this case, 2.71 moles of barium hydroxide. So barium hydroxide is my known compound. I highly recommend that as you're doing this, you write out your chemical equation every time, you balance it. And then when you identify what your known is, you need to circle it, underline it, put a box around it, find some notation system. I know a bunch of you have huge packets of colored pens, and so even though we're not together, you can certainly use those colored pens and identify what your known is. And then likewise, you need to figure out what your unknown is. So notice both our known and our unknowns are reactants here. So this is the kind of question that's an ingredient question. If I have 2 cups of sugar and I'm making a batch of cookies, how many cups of flour do I need to go with that? And so once you have your known and your unknown set up, we're going to build our game board. And so remember, your given information always goes in the top left. And to convert from barium hydroxide to phosphoric acid, we're going to use that mole ratio 3 to 2. And so you need to think about which of those two is going to go on top. Is the 3 going to go on top, or is the 3 going to go on the bottom? And if you take a second to think about that, hopefully you'll come to the conclusion that that 3 moles of barium hydroxide has to go on the bottom. And notice in our conversion factor here, the units are both moles. So if you don't label each measurement with both a unit and the substance for which you're referring to, you're going to have a hard time doing this conversion step from your known to your unknown. So we have 2 moles of phosphoric acid on top. We have 3 moles of barium hydroxide on the bottom. And if you multiply across the top, divide across the bottom, you're going to end up with 1.81 moles of phosphoric acid. Of course, that has 3 significant digits because you have 3 significant digits in your initial measurement. And the mole ratios have an infinite number of significant digits because they're not measurements, they are certainties. It is an exact balancing after counting atoms. And so we would refer to that number 1.81, or both of those numbers really, 1.81 and 2.71, is what we call a stoichiometric equivalent. That means equal amounts of both substances, so you exactly use both of them up and there's nothing left over. And so if we go back to that statement that we have 2.71 moles of barium hydroxide, let's say hypothetically we have only 1.51 moles of phosphoric acid, but we know that we need 1.81 moles. Again, this is like you were making a batch of cookies and it says you need 2 eggs, but you go into the refrigerator and there's only 1 egg. You have a problem. You certainly can't make a full batch of those cookies. We would refer to that thing that we have more than enough of as the excess reagent, because when this reaction is done, some of that barium hydroxide is going to be left over. And that thing that you're going to run out of is called your limiting reagent. You can produce no more product than your limiting reagent allows. So we will not react all 2.71 moles of barium hydroxide, and there will be a little bit of barium hydroxide left over. All right, let's talk about the stoichiometry map, because this is really the central feature of everything we're going to be doing here, and you really, really need to get this imprinted in your brain. You need to be able to recreate it from memory. And so we're going to look at the map. I'm the map, I'm the map, I'm the map, I'm the map. So we have this link between known and unknown, which is the mole ratio, but we very rarely in a lab situation measure things in moles. Usually, if we have solids, we're going to go ahead and try to measure them based on mass. If we have gases, we're going to measure those in volume. If, of course, we're at standard temperature and pressure. And then, of course, we can also do the conversion to representative particles. If we measure some known value in mass and then convert it to moles, we can then figure out how much we would expect to, say, produce of one of those products using the mole ratio. But of course, to verify that, we're going to need a measurable quantity again, so we might then need to convert that to mass or to volume. We can do the volume collection as a calculation, but there's certainly a way to a standard way to determine how much volume of gas is being produced in a particular chemical process. So if you look at the image popping up on the screen here, you have this green liquid to the left with some solid in there. You can see bubbles coming off the solid. This is likely a metal being reacted with an acid, which typically produces hydrogen gas. And if we direct that hydrogen gas via the tubing there into an inverted tube there that has volume graduations on it, we would start with that tube being completely filled with water. And as the gas bubbles in, it's going to displace the water. And as the water is displaced, you can measure the volume of gas that you're collecting. So we would certainly get a known quantity of gas collected from that reaction. But then we could also do a stoichiometric calculation to measure what we would expect to produce from that reaction. Of course, you're not always at standard temperature and pressure, but you could certainly know what adjustments to make if you know the temperature and pressure. So we could figure out the pressure certainly by having a barometer in the room. Or we could just put or in addition to that, I should say, we could put a thermometer in that water, and then we would also know the temperature. And then similarly, as we did on the left side, we can do a conversion to representative particles to figure out how many molecules or formula units we're producing from this particular reaction. Our conversions are well known: 1 mole over the molar mass, 1 mole over 22.4 liters, and 1 mole over 6.02 times 10 to the 23rd. On the unknown side, it would be the same set of conversions. We would just flip them with the 1 mole on the bottom. It wouldn't take a whole lot of time to try and memorize whether the 1 mole goes on top or the bottom when you're on the left side. Simply when you set up your game boards, again, look at those diagonals. But one of the other things I want you to notice is that when we use the mole map was a two-way street. I could go from mass to moles or moles to mass. The stoichiometry map is intended to be a set of one-way streets. So notice the errors, and you're going to start in one of those 4 boxes on the left. You're going to end in one of those 4 boxes on the right. And so everything is one way, and those conversions then are set. All right, so let's talk about how we're going to use this. Here's our same reaction, the barium hydroxide and the phosphoric acid. How many grams of barium hydroxide are required to produce 247.3 grams of barium phosphate? And so again, you're going to start with your balanced chemical equation, which we already have. And then you're going to identify your knowns and your unknowns. Well, this time our known is a product. And so essentially what we're saying here is, if I want to produce this much product, how much reactant do I need to start with? If there are 35 kids in my class and I want to bring cookies for my birthday, and I want to have this many cookies, how many eggs do I need to start with to make enough cookies so that everyone can have one? And so our unknown then is how many grams barium hydroxide. So barium hydroxide becomes our unknown. So we're wanting to know, what ingredients do we have to start with in order to produce some known amount of product. Once you've identified your known and your unknowns, you need to check the map. So where are you starting on the map? Where are you ending on the map? Where I'm starting with a mass of my known, 247.3 grams of barium phosphate. And I want to know how many grams of mass of my product. This is a pretty standard stoichiometric calculation, and it's known as a grams to moles to moles to grams calculation. If you follow the map, each of those arrows turning blue then represents a conversion factor. So we'll start with our given piece of information in the top left in our game board, and we're going to have 3 different conversion factors. And so, next step then is to set up your game board. Put your given piece of information in the top left. Make sure you label it with unit and substance. You should maybe take a break now, pause the video, and you're going to need 2 different molar masses, one for each of those circle substances. So you should go ahead and pause the video and calculate those molar masses. And maybe you would just write them next to those substances on your chemical equation. All right, if you have your molar masses, then our first step is to go from mass of known to mass of unknown. And so you'll have 1 mole equal to the molar mass, and you need to think about whether or not that 1 mole goes on top or on the bottom. Of course, we need grams to go on the bottom, 601.93 grams of barium phosphate, 1 mole on the top. That gets us to moles of known. Our next step then is going to be the mole ratio. 3 moles of barium hydroxide to 1 mole of barium phosphate. Again, look at that diagonal to determine where the 3 goes and where the 1 goes. You should get 3 moles of barium hydroxide on top, 1 mole of barium phosphate on the bottom. Our next conversion is to go from moles of unknown then to mass of unknown. So we're going to need that 1 mole of barium hydroxide on the bottom this time, and then the molar mass is 171.35 grams of barium hydroxide. So if you look at the units that cancel, grams of barium phosphate, the moles of barium phosphate, and the moles of barium hydroxide, and you're left with grams of barium hydroxide. If we go back to the problem, our question embedded here is how many grams of barium hydroxide are required. So multiply across the top, divide across the bottom. This would be a great time to pause the video, grab your calculator, check and see if you can get the answer here. Okay, and so you should get 211.2 grams of barium hydroxide. We're looking at 4 significant digits because of that 247.3. Both of our molar masses have 5 significant digits. So the steps to stoichiometry. Every single time you do a stoichiometry problem, you should run through this set of steps. So the first is to balance or determine a balanced chemical equation. You want to know what equation you're working with. You need to get your formulas correctly written. You need to get your formulas correctly balanced. Those are your mole coefficients, and of course the mole ratio is kind of the connective tissue of stoichiometry from known to unknown. And then of course you need to identify those knowns and those unknowns. So again, find some system, circle, underline, squiggly lines, find something that is going to, and use it consistently so that it will recall what those things mean to you. And then you need to check the map. Don't skip this step. A lot of people do more steps than they have to do because they don't check the map. Where are you starting? Where are you ending up? Every single one of those lines connecting a box is a conversion factor. So you need to think about how many steps it's going to take. And then go ahead and set up your game board. Get your given piece of information in the top left. Work through the game to cancel your units until you get the final unit that you want. Run your calculation, multiply across the top, divide across the bottom. Remember, if you have more than one number in the bottom of your calculation, make sure you hit divided by each time. And then don't forget to check your answer. Check it for units, check it for sig digs, and does it make sense? You need to look at what numbers are on the top and on the bottom. And so if you've accidentally hit multiply when you meant to divide, you're going to end up with a much bigger number than you would expect given what you started with. Okay, so let's try one more. Here's a problem. It'd be a really good time. Again, go ahead, read through the problem, stop the video, see if you can work yourself through the steps to sort this problem out. Okay, and then if we're working through the steps, we start with a balanced chemical equation. Remember, fluorine is diatomic, so you have to have that F2 there. We identify our knowns and our unknowns. We know how many moles of fluorine we have, and we want to know how many liters of dinitrogen tetrafluoride we're going to produce. Check the map. Where are you starting? Notice this time we're starting at moles of known. This is going to be one last step. than the last problem that you saw. And we want to know how many liters we're going to produce. So another thing I want you to notice here is that you did not circle mass on either one of these. So at no point during this problem are you going to need a molar mass. So you don't need to take the time to stop and determine those molar masses. Okay, set up the game board. Given a piece of information in the top left, our first conversion is that mole ratio right away. It's 5 to 1. So we need 5 moles of F2 on the bottom and 1 mole of N2F4 on the top. And then our next conversion is the volume conversion. That 1 mole is going to go on bottom, 22.4 liters is going to go on the top. You're going to cancel out your units, multiply across the top, divide across the bottom, and you should get 14.8 liters of N2F4. So there you have it. Those are the basic steps and processes to stoichiometry. You should go and find your homework assignment and try a few of those on your own.